Yeah, the recording is started.
Okay. Hi everyone. Welcome to ST Skills. Just an intro, like for those who are new, like this is a voluntary-based non-profit organization. The best thing to learn or to get prepared for interviews is to you learn a concept and try to teach. So you go deep and make sure that when you try to present, you gain a lot. So I personally experienced this based on like last so many sessions I gave in the past 1 year. And if you have to sign up for presenting some topic, you can always uh, join the Discord group and present your interest there. So this is today we'll be talking about transactions. This is a continuation of um, the topic that we picked, the transactions chapter in designing data intensive applications book. So in the previous session, like we talked about what is ACID, and just to summarize, like atomicity, it just is a guarantee, just making sure that like if you have multiple um, updates or deletes or like multiple steps in a transaction, atomicity guarantees that either all of them happen or none of them happen. That's a guarantee. And durability is once the transaction is committed, like the data is not lost, like it's permanently persisted to the disk. And consistency, we have seen that database together with the application, we defined when the data is in a consistent state, like either before the transaction or after the transaction, not during the transaction. So how do we ensure consistency? And the last thing is isolation. So this is a guarantee that like if you have multiple concurrent transactions, isolation is more about concurrency. Like if you have multiple transactions reading or writing data at the same time in a database. Um, so this guarantee makes an effect that like as if they're executed serially one after the other. So in isolation, we have multiple levels. So read uncommitted, which is just like you read uncommitted data, and most people won't use that. And we start with at least the basic one, read committed, where you read only the committed data. So which means you avoid the dirty reads and dirty writes. And there is another one called repeatable read or snapshot isolation. They both are different, except that different databases implement like some databases implement repeatable read and some databases implement snapshot isolation, but they both are almost similar guarantees. So the issue that they avoid is, in addition to read committed, they also avoid read skews. So we have seen like what a read skew means previously. So it is just an issue like where if you have a long running transactions, like read only transactions, like if you are taking a backup of database or like some long running analytical queries, so where you read the data, the same data in different points in time, so that like if you see as an aggregate or a single snapshot, then it's not like the correct data. So to avoid that, you have to use one of them. So today we will actually go through what are all the issues that could occur in both of these isolation levels. So these are the three here, and the serializable isolation level. So this is the strongest isolation level that any RDBMS or databases can guarantee at this point. And how it's implemented. So one of them is two-phase locking. We also have some other two implementations which we'll talk about. And there is also, we'll also briefly talk about, since we are talking about transactions, nowadays, like we also need to know about like how to implement a distributed transaction. So with that, let's get started to one of the issues that we see in repeatable read or snapshot isolation. So it's called as lost updates. So this lost updates is like if you see the previous isolation levels, like they mostly guarantee that like if for reading purpose, like if you are reading some data, they always make sure that you are reading the data which is committed, or like avoiding the read skews and all. So it's mostly like looking on the read perspective. So when other writes are happening, but lost update is as the name indicates, like if you have a two transactions, P1 and P2, both attempt to say if we have a database and some table, let's say X value, so they both read the data at the same time, and they both say increment, say x is equal to x plus 1, and this transaction also does x is equal to x plus 1. So if this value was like 5, if they both execute in the same time, then both will get the value of 5 to them when they read, and when they increment, so one of them, whichever runs first or like later, that will override. So say this will increment 6, and this will also have value of 5, so it will increment to 6. So if this is running first in the execution order and this is running second, then this value will override this one. So which means that the two writes which are happening in the same time, whichever happens or executed later by the database, that will override the previous one. So one of the update is actually lost here. So that's the issue of lost updates. So one of the ways database try to prevent this is using like atomic increment updates, or like so if you see an update query where like some data, I think some or most databases allow this. So update table where like set some value x is equal to x plus 1, and you give the where condition where key is equal to whatever the primary key. So in this case, like it uses the existing value in the database and try to increment 1. If this one is executed, this would have already been to 6, and if this is executed, then since it has a value of 6, it increments to 7. So this is one of the approach. I don't know like how many databases support this kind of atomic update, and the other ways like how this last update is addressed is like if you are suppose you have a transaction begin, what you can actually say is like you can use the select whatever star from table. I'm not writing the full query, where you give the condition key is equal to whatever the primary key, and you say for update. So if you use a for update, the databases exclusively log those rows which match certain condition. So in this case, this is a way where like application developers like are making sure that like the rows which they are updating, they always try to exclusively lock so that no other transactions can access or update them at the same time. So if you use for update, it actually obtains a lock on those rows. So only transaction which obtains this lock first, they'll be able to succeed. Then you do the update, and then you can do the commit. So this is one another way how this is addressed. Yeah, I think I don't know if we have another way where this is addressed, but these two are like the main approaches, I think. Any questions on this so far?
Can you please repeat the second approach?
The second approach is where like you in your transaction, when you begin your transaction, you use a select query to obtain the records which match you. So you know which records you want to update. your transaction, update or delete or whatever the manipulation you want to change. So you use the select query matching those condition, and you say like after the select query, I mean like you say that you are selecting them for update. Then you have other update or delete or whatever the insert commands you want, and then you finally commit. So this is part of the transaction you specify when you say for update. It actually databases obtains logs on rows. So like your transaction will have the lock on those rows. So only you will be able to see.
Okay, thank you.
What was the approach one? I'm not sure if that was discussed earlier or not.
Yeah, the approach one was it's basically some databases support like without specifying the value. Suppose if you just look at this, we are saying that set in the update, whatever the table, we'll just say set x is equal to x plus 1. So if you, when they specify that, like it internally takes whatever the value that is their latest at that point and use that value to increment. So you're not specifying, you're not reading at this point, you are only issuing the update without actually reading, like in most other cases. This normally happens in read, modify, write. That is the pattern of like this general problems, right? Read, modify, and write. So these are the normal steps where these lost updates tend to happen. So, but if you see this approach one, like the databases support the direct update commands without reading, where you specify x is equal to x plus 1 means like it uses the whatever the current value you are incrementing just. So you don't need to read the value.
Okay, yeah, got it.
So this is one of the approaches, and I don't know how many databases support this, but like this for sure, like all databases support this method for update. And this normally works, like this update normally works where like for increments and other stuff. But let's say if you have an example of where like you have a wiki page and both users are downloaded the same content and editing at the same time. And when one updates or like when the second person updates, they can easily overwrite the first person. So it's not straightforward even for update to be used on the wiki content. So I think there are few databases which also support another form of update where you say update whatever the table content, and you can set the whatever the new content. Let's say only if this where condition matches like the old content. So whatever the old content that you have read, so only if that condition matches, update this new content. Suppose if one person has read, like two people are editing the wiki page at the same time, and one person has committed, and for the second person when he is committing, this old content condition will not match. So this update command will have no effect on the database. So it just simply runs, and since the where condition doesn't match, it doesn't update anything. So so in those cases, you need to make sure whether your update command actually returned the success effect or not. So that means whether it really updated your row, like one row or not. So if not, like you need to retry by getting the new content and again updating your content. So that's one of the some databases support this where you can actually pass whatever the content that you have. I think it's just a workaround. Most databases support this also.
This is similar to there is this functionality e tag, right? That when you read something, you get the e tag, which is the hash of the old value.
Yes, yes,
So
yes,
when you
correct, correct.
update, you
Mhm.
specify. Yeah, yeah.
Yes, yes, in S3 terms, yeah, it's E tag. Yeah, or like even in. So you can, so for the, in the wiki page context, as you were saying, like E tag, so this whole content can be hashed to a single value, and you can just compare the hash, where as long as the previous hash is equal to this, update my new hash, like the new content. So this is about last updates. And if you have no questions, then we can get on to the Write Skew. I'll erase this. Okay. So the next issue that I have is Write Skew. So the Write Skews are not like straightforward. This is something like databases for them, like it's hard to find. So one of the example, like as mentioned in the book, is like if you have a scenario where like you have three on-call doctors on duty. So let's say you have, the requirement is for you, like of all the on-call doctors, you at least need to have two on-call doctors at any point of time in the duty if you have that condition. So let's say if the, whatever the doctor on call, let's say he's a person one, person two, or even let's use John. So he's on call right now, he's on call, and this guy is not. So let's say if we have a table, I think, hope you guys can see. So this is a doctor and this is on call. So I'm just given like 3 persons, and these 2 persons are on call right now. So your requirement is that like you always need to have two of them on call or like on duty at any point in time. So if it happens that like if Alice and Bob's decides to go on um, or they want to take a leave, sorry, I think the minimum condition is that at least one person needs to be on call. So since you have 2 persons, like if one of the person needs to is sick and if he needs to take a leave, so he can actually what the condition, since we have the minimum condition of one at any point in time on call, so he just queries and like one, we can have two transactions where this transaction is from Alice and this is from whatever the Bob. So when this transaction, he actually reads, so how many people we have, select whatever the count, where on call is equal to true. And just need to, I forgot to add one column. So you will also have some shift, which says these people are all on the same shift. So you can also where on call is equal to true and shift ID, whatever you want to make sure. So they all belong to the same. If the count at least is greater than or equal to 2, so which means that one of the person, now this Alice who is trying to check, he just makes sure that is greater than or equal to 2. So he can go ahead and take leave. So he updates his on-call status to false. And similarly, he will commit this transaction. And if you have Bob, where he's also doing the same thing, he also checks how many people are on call, it's greater than or equal to 2 since they began at the same time. And at this point, he will also set on call is equal to false, and he will also commit. So what happens when these two transactions commit? So both of them went out of on call. So this also became false, and this also became false. So none of the doctors are on call. So this is a condition where, like, if both of these transactions, you have some certain condition to be met, and that condition is you need to have at least one on-call doctor at any point in time. And when they both began the transaction, they have this condition was true, and when they both finish the transaction, so it happens that like both of them went out of on call, so which was not supposed to happen. So this anomaly is called as Write Skew. Any questions in understanding what this problem was? Then we'll go to how this is addressed.
Can I ask a question?
Yes, sure.
So, like, what you are explaining, and what is the difference between database versioning and this? Because database versioning also does the same thing.
This is not versioning. This is the data anomaly I'm talking about. So the database will version, or like it will always have the data. So after it commits, like each, I mean, like it goes to a different state, right? Like, so that the data goes after every transaction commits, the data goes from one state to another state. So if
Yes.
so
I've used liquid base, and liquid base also it works on commit. Like every time you commit it, it will change the state, and then you cannot revert back to that. You need to always upgrade it. That's how
yes.
my understanding is, and that's what we are doing over here also.
Yes, correct. So when you commit, it means that your change cannot be rolled. I mean, like you can roll back after that if you want. Like it's basically the data is there. You need to have another transaction reversing the effect. So which means that you'll have both in the history. So here what I'm trying to explain is, so when you begin the transaction, whatever the condition that you wanted it to be true was true at that point. So the condition that we had was like at least one on-call doctor was supposed to be there. Sorry, at least two when we begin this transaction. So at least this doctor can go on leave or like sick leave or whatever. So he can go out of duty. So this was true at this point, and similarly, like there is another transaction which is because of the effect of another person. He's also checking the same condition, like how many on-call doctors. So at this point, this transaction is not committed. That's why you have still greater than or equal to 2. So he also updates his on-call status, and this guy also updates this transaction, also updates on-call status. So when they both commit, so whatever the condition that was true at this point, at the commit point, they are no longer true. So I'm just saying that this scenario will happen if you don't, I mean, like if you are using the previous, this one of these two isolation levels, and if you don't normally, from the application standpoint of view, or like from your logic, if you don't carefully monitor this, so at this point, whatever the condition that was true at this point will no longer be true when it is trying to commit, because the other guy has an uncommitted write, which is updating this condition, and similarly for this person also. So don't look in this from the versioning perspective. So this is just a data anomaly which can occur if you don't normally either use the highest serialization, which most people won't use because for performance reasons. So you just need to aware that these anomalies can occur in databases when you're using those two, and have a mechanism to address, or at least use higher isolation level, at least for those.
Okay, thank you.
So this anomaly, as I said, like lost updates or write skew or like the phantoms, which I will talk about now. So this all will occur if you're using either repeatable read or snapshot isolation or read committed, one of these isolation levels. So I'll also explain what a phantom is. So then we will get into like how this can, or like let's go. So the phantom is basically just if you see at this point, whatever the condition that you have at this point is no longer true at this point. So when you commit this, so whatever the select condition that another transaction have, so this data will whatever the other person, other transaction selects or read-only queries with some conditions will have an effect if one of the transaction is updating. So basically the phantom is an effect where if one transaction is updating or deleting or making some updates to the database, and that will indirectly have an effect of another transaction where it's trying to read the records for update or delete. So this update of where one transaction affecting another database rows or like interests of update. So that effect is called as phantoms. So there are more examples apart from this write skew for phantoms. We will actually even more examples of write skew. We will look into one by one and see how we can address. So any question on this write skew at this point? Okay, I'll take it as no. Okay, so some of the other examples of where the write skew can occur. So here, at least in this condition, you know that your select queries are actually returning the data. So which is at least the count of two records or two records at this point. So let's take another example where like this may not be true. So in this case, like if this is returning some data, you can always use for update. So to explicitly log those rows so that you can make sure that so when you commit this both rows, like both Alice and Bob are logged by this transaction. So when you use for update class, so even if this guy is running parallelly, since this guy has obtained the lock, if we happen to run first, so this both rows are locked. So this guy won't be able to obtain the lock if he uses the same for update. So he will actually wait for this guy to finish, to commit, so which will change this condition now. Instead of 2, it will become 1. So this is how this write skew can be addressed by using for update. So, but like there are some conditions where this won't be true. So, but before explaining another examples, I just want to make sure that you guys all got what I was trying to convey here.
So, Naga, you are saying when we invoke the for update clause in the SQL, it not only blocks the rows that we want to update, but it will also block the rows that we have read. Is that
Yes, correct, correct. So whatever the where condition or like the select where clause you'll have, right? So you just, that's why you just need to be very careful or cautious when you're using for update, because if your condition is broad enough and has more rows than you really want to log, then it can significantly affect the performance because many other transactions will be blocked because of your for update class. So since the anomaly is actually considering this to all the people, like in this case, at least 2 people who are like, imagine if you have more than 2 people on call, you can actually only log 2 people, not like most of them, because your minimum guarantee was only 1, right? So in this case, we have both people who are on call, and we have a minimum guarantee of one who needs to be there even after the commit. So that's why if you use greater than or equal to 2 and for update, you are locking both Alice and Bob entries, so that like if Bob is trying to do the same thing, he won't be able to do because this guy is going out of shift. So when he commits, so since this transaction was waiting on the same clause, the same select condition, so he will this effect will now be changed and reduced to 1. So he won't be able to do this. He won't be able to go out of shift, because if he goes, he will violate the whatever the agreed promise or clause. So that is one way how this can be addressed. And but like there are other scenarios which I will talk about now where you won't be able to use for update.
So now this for update is blocking the row completely. Is it creating a lock? I didn't
Yes,
get that.
yes,
Like
correct.
how
So in database, when you use for update, it actually locks all those rows which are matching this condition for writes.
okay.
Others may be able to read, but they will be blocked for writes.
Oh, okay. So the for update is a keyword?
Yes,
Or-
correct. It's a keyword in SQL.
Oh, okay. So we can lock a specific. So your main idea is instead of giving high level data isolation, we are trying to handle that data anomaly issue, right?
Yes, yes, correct.
Okay.
So suppose if you this can be used like if you are using repeatable read or snapshot isolation or read committed, and you want to get over this anomaly.
Oh, okay. Okay.
So if you are using serializable, this for update is not necessary because that's already very pessimistic. It uses multiple locking levels already.
Yes. Okay.
Okay. So we know this example of Write Skew anomaly can be addressed using for update, but there are like other examples where you may not be able to use this. So that example is like, can I erase this? Leave this. So another example is a, let's say you have a meeting room booking system. So you normally have all the bookings to which already the reservations have already been made. Suppose you have the room and whatever the time duration, time begin to. So let's say the room 101, you are booking from 12 to 1 p.m. So similarly, like for the same 101, you can have 10 to 11 or so like this will have, right? So you have a meeting room. So this entries will be there for all the past reservations. But let's say like you want to book for some time, like in the future, you want to reserve a meeting room booking. So the same 101, you want to book sometime in the future, like if you have the date also in this time. So if you want to book in the future, so this condition, like you normally check if the select condition where the room is equal to whatever the room that you are interested, like 101, and the start time is equal to whatever the time, let's say 6, I'm using shortcuts, 25, and 10 a.m. and end time will also use, right, 6:25, so let's say 11. So this condition, you just make sure that this doesn't return any rows. So your expectation in the beginning of transaction, if you want to book this meeting room for this duration, is that when you run these queries, it should not return any rows. So only then you try to go and book this meeting room. So update for this time duration, and this time whoever booked, maybe you'll also have some other parameters. You update this transaction and you commit. So here you won't be able to lock explicitly, right? Because your database hasn't returned any specific rows. So this is sometime in the future. So you won't be, so this, if you have multiple transactions, if two people try to book the meeting room at the same time, and let's say even this other transaction, which is trying to update, so this guy also will get 0 rows. So he will also update and he will also commit. So you have a scenario where like two people book the same meeting room for the same time, and both of them met this condition. So how do you actually address this? So this is an anomaly where you cannot use like for update because you don't have anything for update. So, but I think like the databases still can address this kind of things, like using something known as predicate locks. So how this is addressed is like those locks actually belong to certain condition, not the rows. So there is some kind of lock called as predicate lock, so which is normally on some certain condition. So they always so when you use predicate locks, the databases normally attach this lock on certain condition. So if you obtain a predicate lock for this, then when you try to commit, it actually checks whether this condition is still true or not. So for this, it may be still true, but like for the other transaction, when it is trying to commit, so it checks that this predicate is no longer met. So it will abort this transaction. So how this is normally addressed is by using predicate locks.
Naga, can we convert this insert into an update? So instead of inserting something where start time is this and
This is an
end
insert.
time is this,
Not
can we just?
So are you saying convert this insert to update somehow? Yes. So yeah, it can be, yeah. So you can actually do some things like if you want to convert it to an update, like what you can actually do is you can actually try to generate, like for the next 6 months, you can generate all the possible time slots, like every 1 hour or 30 minutes or whatever, every 15-minute time slots. That's a minimum you can book, right, normally. So you can generate for the next 6 months or 1 year, like whatever the duration you normally want to have the meetings normally reserved, you normally allow to be reserved. If you generate and store in some tables already, all this even for the future, then you can actually use this for update again, because you'll be able to find this slot, since you already pre-generated all of those meeting room durations for the next 1 year, as minute as like 15 minutes duration, and maybe even like allowing 1 day or 2 days, like depending on whatever the maximum duration you allow for booking. So if somebody wants to book in 1 hour, so you actually check like the start time is this and end time is this. If it composes like 4 rows in the database, so you can use a select query to get all this range of start and end time, and use still for update. And I think in that case, you just make sure that instead of insert, you can use update. And you just update that those status for those meeting rooms as reserved. Yeah, thanks for asking that. And that is possible for this example at least. Any questions on this another idea which I told?
Is it an alternate idea or it is alternate totally different scenario?
Yeah, so logically, if you are that's different depends on how you implement the meeting room booking system. So suppose
Okay.
like originally if I'm not pre-generating all the rows for the next 1 year, then I won't be able to obtain using for update. So what I tend to do is like maybe use kind of predicate locks where you lock certain condition that, and during the commit you check again that condition is met or not. So so which in case like it meets for this but not for that, the databases knows to abort. So when you use this kind of logs. But if you have an implementation where you pre-generate all the rows even for the future, so you'll be able to obtain the log using for update.
Okay.
I have one question regarding for update. Actually, in the end, when you said that only the lock is created on the write and not for read, I got confused over there. So if when the read happens, if both reads the record as 2, after one does a commit, the other one gets locked. After the commit, it can still go ahead and update it, right? Or does it invalidate that? And if it does that, how does it do it?
Yeah, so normally like it depends on the isolation level that you are using. So in this case, like I think the reads are allowed when this update is happening, even when you use for update. So in this case, like they only would have read like if the suppose if we are using, I don't know what example I was talking about. So the for update actually obtains the exclusive write logs. But depending on the isolation level that you use, like I think the only difference between these two is the read skew. So they almost behave the same way. It allows for reading, but when you want to write, that's where it actually checks whether you have the latest copy or not. So if you are using the read of the previous early updated value, so you'll have a scenario similar to last updates. So if you have read a previous version of the value, but like in this case, since you are using for update and this is exclusively logged, only the transactions which are started when this transaction began and obtained the lock, or like in the similar time, so only they will be logged or like they'll be waiting on that select condition. Suppose I have another select condition matching the same, like in the previous on-call doctor scenario. So when, or even for this, if I have the rows, so when you use for update, it has obtained the exclusive write lock, right? So this another transactions won't be able to proceed to the next steps and still be waiting on this select statements because he's using, this guy is also using for update.
Okay.
So since this guy is also using for update, you won't be able to obtain the exclusive lock on the same rows which other transaction has already acquired. So in that case, it will actually wait till it can hold the lock, and when it holds the lock, his condition of 2 doctors would not have met because now there is only 1 doctor because this transaction has been committed. So if, as long as you use for update, you will not have issues like when for other transactions. But if you don't, then it will be similar to last updates.
Yes. Okay. Yeah.
And Naga, I understood the concept of that repeatable read snapshot isolation, but I don't understand the meaning of that word repeatable read. Like, what does it mean? Like, I mean, that question came to me now after 1 week. But I mean, what is repeatable? What does it do there?
So the basically, I think maybe the idea where the name actually came from that IBM system R, That's where like whichever the systems implementing that specification, I think they all got this name. So this snapshot isolation, I think, was from some other 2000s, like I think Postgres or some databases which are implementing that will actually get this. But this repeatable, I think the name came from the fact that if you have obtained a snapshot or like the point in time state of database, even if you read like multiple times, if there are no other transactions committed, you will always get the same data. I think that's I'm thinking that that's maybe the idea behind the name. So, but like I think if you look at the previous read committed, you'll have the examples of read skew, right? So if you are reading in multiple times, you are not getting the same snapshot of the data at different points. So that's where you'll have the read skew, so leading to an inconsistent snapshot or copy. So
Yeah. Hey Naga, Deepti.
you can add. I think you can.
No. Yeah, I think. I mean, you are explaining. Just want to reinforce that. So the notion of this term repeatable, right? The idea is exactly what it's literally saying there. So if you read some data, right? Let's say transaction T1 reads some data, and T2 comes in and modifies that data and then commits, right? And then T1 reads again. So it will get different data for the same query, right? So, but the idea is that how to, depending on the scenario or isolation level, I think you want to, whether you want to ensure repeatable reads or fuzzy reads, I think that's where the name comes in, that getting consistent like data for the same query. But yeah, I mean, this is, I think it's more like I need to refresh it as well, but looking at the term, I believe that's what it means.
But who is going to read it again if there is no parallel transaction going on?
Yeah, I mean, like if you see the long-running queries, like analytic queries, or like if you're taking like full snapshot of the database, you don't want like transactions updating and like if you have multiple transactions updating, and if you are reading, like say at this point you are reading this section of data, and by the time you read this data, you don't want these tables to be updated because that's not like a single point in time data, right? So you're just making sure that you're reading the consistent view. So I think this normally happens when you have long running queries or if you're taking a snapshot of your database. That's where you want to make sure that if you start reading, like from that point, like though you read multiple times, irrespective of the following committed transactions, you want the same view of the data. So
yeah, right.
And is the dirty read exact opposite of the repeatable read then?
no, I think that the dirty read is even worse. Like it's actually you are reading the data which is not committed yet.
Yeah.
So if there are so at this point, like I haven't committed, so you have updated some data, so other transactions will be able to read this data. So which is the worst, like you don't want any application to have that scenario. Like otherwise, I think, I don't know, where there may be very few applications which want this kind of things.
Yeah, usually default options, they tend to have read committed. So they want to avoid dirty reads because that's definitely, not a good model.
Yeah. So these two are very bad to have in any application. That's why most applications, at least at a minimum, use this read committed.
Yeah. So like Naga said, a dirty read comes in when a transaction is reading data which is uncommitted, and repeatable read is like another transaction committed data. But like Naga explained, that if you have T1, which is a long running transaction, and it's reading data at 2 data points, but between those 2 data points, another transaction came in and updated something and committed it. So then T1 will get different views of the same data.
So yes, so here, yeah, we are talking about, though you have committed transactions later, you will always be able to read the same view of the data. Yes.
Right. Is that mean in a long transaction, if while reading the data, if there are some other transaction commits some data, those newly committed data also will be available with repeatable read isolation level. Is that right understanding then?
No, suppose if this transaction started at this point, like this transaction, this T1, which is a long running read.
Okay.
So if this started at this point, you'll have some snapshot or like some view of the database until this point. So you can have T0 or T3 or whatever. If you have some another transaction which comes and updates like T4 here, and this is still running, and this T4 finishes here. So this, whatever the T1 is reading will not have the view of T4 updates.
Okay.
So, but if you use read committed, I think it will still be able to fetch T4, though you don't want it. Like if you are using a long running transactions, you want the same view. So if you are updating something, then like we have seen the example of account balance, right? You are transferring from one of your accounts to another of your account. So at any point, like your total balance should be same.
Okay.
So if you have, suppose at this point, this is to transfer from one of your account 1 to account 2. So suppose like at this point, like if both balances are like even, and like we have seen that example, right? So if it's somewhere in between, like this is if you have two transactions updating this, so one transaction updating the source account, one updating the destination. So this updated and reduced to 400, but there is another T5 transactions which is incrementing this to 600. And if you have read this point in data, like if you read at 2 points in data, so you may have read 500 and 400 here, like from the T1 standpoint, where you actually wanted to read 400 or 600 or 500 and 500. Was that clear? Or?
Yeah, kind of. At least I got some idea. I can.
Yeah, basically,
more,
yeah. So you can have, this is one just example. So there could be another examples where like you have multiple transactions updating some state here, some state later, and then like you don't want the view that you are looking to be continuously updating, right? Otherwise, you won't have a good snapshot of your database.
Okay.
For backups. So
because my understanding was read committed means even the transaction starts, if anything getting committed after that, it won't care. Whatever is there at the moment.
Yeah. At that point, correct.
Oh,
Sorry.
okay.
Yeah, correct. That is correct. But
okay.
I think to explain repeatable write,
oh, okay.
Example.
Sure. Oh, okay. Sure. Thank you. That makes sense.
So we have looked at the condition of even the meeting room bookings where like you have the scenario of where you won't be able to use for update, and there is some mechanism called predicate locks which can work in this. And phantoms also we have seen, right? I think let's look at few more examples. So meeting room is one, and if you this is something which everyone can relate to. Suppose you want to claim a username on any like Gmail or like any place where you have usernames. If two transactions are trying to claim the same username, then like you'll have the similar example, right? You won't have any entries. So you won't be able to even use predicate locks for usernames. I don't know, because for this at least you can actually generate some rows and even have for update. I think for username scenarios, I don't know if predicate locks can work or not. I think it may work, but it can be easily addressed using serializable. So usernames is one example, and multiplayer games are another example, where like multiple people are trying to move to the same position in a battlefield, or like but like however we notice that like all of these anomalies follow this common pattern, right? Where you always have this select condition where you're trying to check whether something is there or not, whether this username or whether the meeting room select star from whatever the table where condition. So you always have this select, and you have this update, insert or delete, whatever you want to do, and you have the commit. And you always know that like at this point, whatever the condition or a premise, whatever you term it. So this condition, which was true at the beginning of the transaction, is no longer true when it's trying to commit. So that's where most of this anomalies trying to occur. So all these anomalies can be addressed. You start using serializable isolation level. So all these three issues will be you can get over easily, including the phantoms. So the phantoms, as I explained, like it's just an effect. If you are committing some data, this commit will have an effect on some other premise or condition, like some other transaction commits. So the effect of where one transaction updating the premise of other transaction, that's called phantoms. So yeah, it's also similar to Write Skew, but like that effect, I think it's called as phantoms. Yeah, any questions on this before we get on to serializable isolation level?
Naga, where is this predicate locks used, like specific database that you're talking about? Because we don't have in SQL Server.
I think, let me quickly check. I don't know if the example or
I think it's a internal database concept.
it could be internal database concept, because or maybe how serializable is handling this Write Skews. Just a minute, I can clarify real quick. I don't know where I read that. Yeah, I can clarify that. I think it may be on like how this serializable is handling. Don't know where I able to. Yeah, I think it's on how the two-phase locking works.
Okay.
It could be one of the conditions. Yeah, I was wrong.
Thank you.
So it's basically whatever I explained on how the predicate locks are used. That's how the serializable handles these issues. So I mean, like, to avoid the phantoms or Write Skews, all we want to do is like one of the ways of addressing is like how the serializable is handling or using the predicate locks to address these issues. So yeah, thanks for asking that.
Thanks, Naga.
So the serializable, as the name is, I don't know. So this is the strongest isolation level that all databases offer, and this is where like the name actually truly comes into effect. The name, like we give the definition of isolation, right, as like the transactions will have the same effect as if they are executed serially. So that's truly brought into practice by Serializable. So this will just make sure that all the transactions will have the same effect as if they are executed one after the other, or like the serially, like T1 and T2 in this. Though they both begin at the same time, it will have the effect like T1 can be executed first and then T2 can be executed next. So there are like three ways on which the serializable can be implemented. One of the ways is literally executing in serial order, and the second one is like two-phase locking, and the third way is SSI. This is actually serializable snapshot isolation. So these are the three ways in which like the serializable isolation is implemented by most databases. So the first one, if you look at the serial order, like the actual serial order execution, so this is where like this is normally implemented by database such as like I think Redis or like even H store, or there is Vault DB, I think. So the idea is like you have single thread which is executing all this. Let's say whatever the writes that you want to do, you will have a single thread which is executing all the writes. So the idea of this serial order is like, or the requirement for this to for this serial order implementation is that your entire data set need to be fit in RAM. So all the data set, or like whatever the data that makes sense for the transaction, if it can fit inside the RAM, so you can have a single thread or like single CPU, like one single core CPU, which is accepting the writes. So you don't have the issue of multiple threads trying to obtain lock to write. So it's only single thread which obtains access, or like which can which accepts the writes and updates the data in RAM, or like you can even have persistence here. But like when your process or the database process which is using normally uses single core, so you'll have all the transactions running through the same thread. So it is literally executing one after the other in actual serial. So there are few databases, as I said, like VaultDB. I think Redis also for some versions of implementation uses this. So the advantage is that like it can easily fit into RAM, and it's mostly works for small data sets. And if you don't have too many concurrent transactions, and if your load can fit into one core CPU, then maybe this is the simplest implementation you can have for serializability. And yeah, as the name indicates, like if you are using single CPU, you are limited to the bandwidth of the CPU, how many transactions it can handle at this point in time. And you're also limited by the amount of data that you want to manipulate or work on. So which is like nowadays you have many databases, right, in memory databases which can fit into the RAM. So there, if you have some concurrency and you want to benefit from serializable, you can choose databases which work this way. And the next one is two-phase locking. So this two-phase locking acts as a pessimistic. It assumes that like anything can go wrong in this. So the locks are very strict, like in two-phase. So the name two-phase comes from the fact that in the beginning of the transaction, like which is a phase one, it obtains locks for all the rows that you are obtaining, and in the commit phase, like which is the phase two, it actually releases the locks. So that's where this name comes. So whatever, whether you have the rows in database or not, as I said, like there are a few scenarios we have seen, like where the rows won't be even present, for some transactions which have some range in the future, like there it uses the predicate lock concept, this two-phase locking. So at phase one, it obtains the locks, and phase two, which is where like after the commit or abort, whatever it happens, it releases the locks. So that's why it's called like two-phase locking. And yeah, and if you are using this, it's basically since it exclusively locks all the rows that you are putting in this select, you need to be very careful on what is the condition that you have. If this range has a large range of rows that you are selecting than necessary, then your database performance can be hit very hard. So where you cannot have many parallel transactions being run at the same time, and you are locking from other transactions which could update some other rows parallelly. But so you just need to be careful around this condition, like how you define. So, but this is how generally this two-phase locking works. And even the predicate locks, which I have explained, like how those write skews or phantoms, or they're addressed. So they are used in this scenarios. Like in the phase one, it obtains the predicate locks matching that condition. And during the commit phase, it actually checks whether this premise still holds true or not. For this first transactions which it may have executed, it will be true. For the second transactions, that phase, whatever the premise that it has, no longer holds true. So that's how this two-phase locking works. We can actually discuss a little more of how this two-phase locking is actually implemented. Any questions so far?
So the two-phase locking also blocks reads, or when read happens also it does the lock, right?
Yes, correct. So so in this two-phase locking concept, like so you normally have there is some concept or some mantra called like in snapshot isolation or repeatable read. Readers never block writers, and writers never block readers till this point of isolation level. But if you come to this serializable, then reads also block other writes, writes also block other reads. So unless you have many other transactions which are happening in read-only mode, that's where this lock can be obtained in shared mode. So as long as multiple transactions are reading only, they can obtain the lock in shared mode. But the moment any transaction wants to make an update, they needs to obtain an exclusive lock. They need to upgrade the lock to exclusive. So this exclusive lock can be obtained by only one transaction. If there are like, yeah, this shared lock can be obtained by multiple as long as they are reading only. Any questions? So
to your point on the previous statement of readers doesn't lock writers, I think that there is a concept of using no locks, exclusive locks being applied when reads are happening on SQL Server. So we use something called no lock when we run any transactions for read. So it again depends on what database and what kind of isolation we are using, and how the locking is used. It's not, we cannot give that generic statement that reads are always, reads allow writes always, or writes allow reads always, right? If I'm not wrong.
I have also heard many DBAs saying this statement many times. Whenever we go to them with the query, they always say this: readers don't block writers. At least with the Oracle DBs said that.
So yeah, it depends on the isolation level that's being configured, or like that's being used mostly in your databases. Like by default, if your databases is operating on repeatable read or snapshot isolation, that's where most databases normally do. So there, like if they say at that point, like if databases say like the readers never block writers and writers never block readers, that's correct until this point. But now we are talking about serializable. So where you have the two-phase locking, right? So at this point, like that condition no longer holds true, because though you are reading at this point, you are exclusively, if you set your isolation level for serializable, you are locking them for update, right? So when you select some rows here, you are actually locking them for update.
So serializable
Normally,
will.
if you have outside of transactions, if you have simple select queries, then even for select queries, they will be obtaining at shared mode. But like the moment they want to update, it needs to have like the exclusive lock to update.
So any DB operation will be locked. Is that what you are saying with serializable?
Yes,
whether it is
at
read
least
or
in
write.
shared
Okay.
mode. At least in shared mode. Though you are doing read only, if you have multiple parallel read only transactions, they will all have in a shared mode. But the moment any transaction wants to update, it needs to go to the exclusive mode. And at any point, like only one transaction can have exclusive lock. So if one transaction is having exclusive lock, other transactions are even barred from reading. So if T1 is having this exclusive lock, if T2 or T3 or whatever other transactions want to read the same data which is in this condition, or whatever this transaction is operating on, they won't be able to read. They need to wait for this lock.
So when your application demands consistency more important than availability, then we may consider this.
Then I think we need to go for serializable.
Okay.
So yeah, so how databases normally implement this two-phase locking is like there are like some locks that we have seen. I already talked about predicate locks. That is for the future conditions. This is for future. And for the existing rows and all, like you can have, if you go for the lock at granular level, is you can go at row, or I don't know, sometimes even columns is possible or not. But like normally you need to have at rows because it's a SQL database, right? So the granular level, you can have an exclusive lock is row. But like if you start operating on for every row locks, the databases needs to maintain lot of logs, and there is lot of overhead. So this having a lock on each and every row and for every transaction, I think is more overhead for databases. So they also use a concept called index range locks. So here, to be safe, they actually try to maybe like if you are using a meeting room booking example, like if you are booking sometime from 12 to 1, maybe instead of obtaining on that specific shift ID, not shift ID, I don't know, the specific booking room, like 101. So you also block, either you block all the this entries, all the time entries for this meeting room, or you just say that like for this duration you block all of the bookings. So they just try to broaden this instead of row level to a little broader because the indexes are sparse, right, mostly. So they try to make sure that like if some transaction is already um, doing some updates on a specific index range, so you normally have this indexes pointing to the actual rows, right? So these locks are at index levels, and if some transaction is already updating some within this range, so you can even have some locks here. And if something is already updating, you can hold other transactions while this other transaction updates or releases this lock. And then so that's how they operate, like the index range locks work. So these are little performant than this granular row level locks, and are easy to manage from database perspective. So, and at the same time, like you don't want this range to go more broader, because that's again you are limiting the amount of concurrent transactions that can happen. So it's kind of some you need to have some sweet spot like index range where you're only locking only some set of rows and not go in too much granular level where you have heavy performance hit. If you go too much broader, you'll have like limited concurrent transactions which can happen at the same time. Any questions on that index range locks?
So index range locks are fine. I have one alternate question. It's like if you do a join on two tables, and if you are updating one of the tables, will the second table also be locked?
Yes, if it's in your select query, yeah, I think it will be locked because that's how this serializable works, right? Like you normally wants to lock. You don't know at this point like how many you really want. Maybe what you can actually do in those cases, if you are joining on other rows, but you are actually okay, you are retrieving rows from table 1, but like you are using some join condition on table 2 to meet certain condition.
Yes.
So yeah, in that case, like you can make sure that like the rows, I mean, like if you are using for update, I think it will be easier to specify because the rows that you get only will be updated. But in this case, the join, whichever is affecting the even other table rows, I think even they will be locked. Maybe if others have a more in-depth idea on this, they can also pitch in. But as far as I know, I think they should lock the other join or the, I mean, like if you're using a join, whatever the tables that you are or the values that you're trying to join, I think they should also be locked.
Naga, but do we need locks? Because we are in serializable mode, only one query is getting executed at one point of time and we are not allowing concurrent executions. Then why do we need a lock? Just let the queries run one by one. Once it's finished, take the next one from the queue.
Yeah, so yeah, that will work as long as you have the single thread, right? Like, but our databases, all our DBMSs are operate on multi-core CPU. So you have multiple threads in your database which are accepting concurrent transactions from different clients, and you are bound to happen like this race conditions always come in picture. Like there are multiple threads which would have accepted different transactions, and they'll be able to figure out and only when they try to update the same piece. So as long as you have this multi-core CPU, you need to have some kind of locking, because for example, like if you look at this SSI, it uses the same snapshot isolation plus some other mechanism to prevent this. So, but like to summarize, like as long as you use the multi-core CPUs, which is what all database servers tend to use because they have they need to they need to offer more connections, or like they need to process more parallel reads or writes. To support that, they need to operate on always on multi-core CPUs. And when you have this multiple threads and parallelism, you always need to make sure that only one thread can access any rows or update.
So then how is it different from the repeatable read and all? Because there also we are applying locks and making sure that only
No.
one thing is
Actually,
locked
yeah,
in.
these anomalies are not accounted in repeatable read. So by default, so this lost updates can be covered using for update class. But if you are having like this predicate example, and or you don't want people to use for update class, so we can't always assume that the people who are developers who are doing from application standpoint, they exclusively lock. What if they forget to put for update? So if for all those strongest consistent data scenarios, you will use serializable. So that's where like to avoid all this indirectly, which can happen in these two levels. So that's where you are going for this all exclusive locks.
Naga, I mean, actually, you can keep transaction level at the multiple transactions as well. I mean, and also
Yes,
the
yes, yeah. I think that's possible. Yes.
And for update also, it runs at a different isolation. Even if you set database isolation to repeatable read, the for update actually doesn't use repeatable read isolation. It works at the read committed isolation. So the transaction to transaction, it differs actually.
Yes, but if you know for sure that if you use for update, it locks the rows that you are actually have in context, right, in the select query. So it is kind of when obtaining an exclusive lock on the rows that you are updating. So it indirectly behaves like the serializable for the transaction alone, like making sure no other transaction try to update. So if you use for update, other transactions cannot get the lock on them or write on them, right? So it's kind of irrespective of the isolation levels here. It always, as long as you obtain exclusive lock, it's similar to serializable in that context.
Okay. I mean, I'm a bit confused on this one. Actually, I mean, the isolate. I mean,
No, but you
yeah.
know that we can obtain exclusive lock, right? I mean, like again, this is my understanding. Others can also pitch in. So when we say for update, if you are updating your whatever the select query rows with for update, you are clearly locking them for your transaction exclusively and not giving any other transaction to update. So you are pessimistic in that case. So if you are obtaining exclusively lock with the select query, so and you have an exclusively lock, so which is what normally happens in serializable also. But like you need not set serializable isolation level for update. But what I am trying to say is, since you are obtaining exclusively locks, its behavior will be similar to serializable, at least for those rows.
Okay.
Naga,
I don't know like if I made sense, but like that's my understanding. You can again check.
so Naga, I am also now confused. So when we apply locks, only whenever we apply locks, the code goes into a serial mode, right? One thing happens after the next.
Mm-hmm.
I mean, that's how it works in the languages. But now here in repeatable read and serializable, how is that different? Because the locks are used at both the places, and we know that lock means the execution is going to be serial at that particular data.
Yes. So yeah, basically here, if you have multiple transactions, what we are trying to say is, if you are locking something and if you are getting a lock in exclusive mode, which means that you are obtaining now we are talking about serializable, right? So if you get a lock in exclusive mode, that means you are updating. So all the other transactions which are happening right now, whether T2 or T3, all of them, if they are waiting for the lock on the same data, that if they also want to update, so then they need to wait this till this guy who is holding the exclusive lock releases. So so it's kind of serializable, right? Like these transactions are waiting for these transactions to happen. So though they came in concurrently, these transactions have threads are indirectly waiting on this. So the effect is like this transaction finished, so it releases the locks. Then one of this T2 or T3 acquires the locks in exclusive mode. Then one of them runs. Again, like it releases the logs. Then it another transaction obtains the lock. So the effect is again the same as if you are using the logs on concurrent programs, right? So the idea is again this indirectly relate to the concurrency and obtaining a lock. Like you are avoiding the race conditions by using the locks.
I
So
think
the effect is same as if they are executed one after the other. Is what is happening the same.
So one thing to add here, in serializable logs, as Naga was mentioning, there is this range lock that we are applying, right? So when you put a where condition or a select statement, it will actually lock a range of rows. So it avoids any phantom reads on that data. Whereas on repeatable reads, there is no such thing called range locks that are being applied.
Yes.
You will still have phantom reads on repeatable reads, but whereas you will not have phantom reads on serializable isolation.
Yes. Yeah, basically all these three issues that I highlighted here can happen in repeatable read or snapshot isolation level. So and by default, and in serializable, all of them are avoided. Let me keep track of time. So I have another one to finish, like serializable snapshot isolation. It's small. Maybe I can finish that, and we also have distributed transactions. Is there any quick question that I can address before going to that? Okay, so it's good. At least like let's finish this SSI, and maybe if any questions, we can always talk in the end. Okay, so the last one is, sorry, I think I erased serializable snapshot isolation. So this works around the same concept of the snapshot isolation, but like comparing to this previous two-phase locking, this two-phase locking is like pessimistic, as I said previously. So pessimistic means it assumes that anything can go wrong, so it obtains a lock in the first step before even proceeding for updates or commits, right? So, but SSI works in optimistic manner. So it assumes that like by default, like things don't go wrong. So let's try to finish the transaction and see if we can complete it. So what happens is, if in the similar steps, like here it doesn't get the lock, but it tries to update. But before commit, it actually tries to check whatever the premise that we have previously, whether that is still holding true or not. So since as the SSI, since this update or whatever the update deletes are actually happening on another snapshot copy, right? That we know for sure. So this updates can happen without any issues. So, but before committing, it actually checks whatever the premise that we have, the condition, is it still holding true? So If it's holding true, it commits. If it's not holding true, that means that some other transactions began and updated the rows which is matching this premise or condition. So at this point, it detects those changes and it actually aborts the transaction. So the idea is, like, instead of being in pessimistic manner, it tries to assume that there won't be any issues. So let's try to finish the transaction. If we are lucky enough and there are not so many concurrent transactions, then most of the changes will be able to commit. So only very few transactions where you have these issues or they're trying to update the same rows, these conditions that we have seen, those for those scenarios. So at that time, it actually checks that this premise or condition is no longer true. So it aborts the transaction. And when it aborts, like, again, the user needs to retry. So any questions on this SSI? I can actually tell about, like, how they normally try to work. So the main thing that SSI needs to keep in mind is if you have multiple transactions, T1, T2, or T3, whatever. So before committing, it needs to find how many other transactions have uncommitted data or committed data. So you have the condition here and updates here. And similarly, condition updates. And if this is committed at this point, then if you are using index range logs, I don't think logs are there, but it knows like which transactions have been committed, right? Like if this transaction committed the same rows, then in the database we normally have created by transaction and or whatever deleted by. You have these two, right? The transaction ID. So it can actually check how if there were some updates already made before any transactions created or updated the same rows which it is trying to update. It can use this data in the database to see if another transactions committed that. If it finds some other transactions updated from the snapshot version, like it will compare to its own version. So if the data is same, then it can actually update. But if this transaction is another transaction which updated, then it knows that some other transaction has updated this same entries. It will try. It will abort the transaction. Is it clear what I'm trying to say? So the behavior is like this goes in the pessimistic way, assuming like anything can go wrong. It obtains exclusive locks, but this doesn't obtain any exclusive locks or any lock concept. It just tries to check that before committing whether whatever the condition that we have, is it still holding true? And that can be checked by checking which all other concurrent transactions or uncommitted data that we have and verifying those entries. So this can be used like the optimistic works like as long as you don't have too many concurrent transactions. Like you can, as long as you have some medium range of concurrent transactions, this still works better than two-phase locking. But if you have too many concurrent transactions, or like if your application behavior is that every time you have this concurrent transactions coming more often, then two-phase locking works better. If you have too many concurrent transactions, you'll have this so many snapshot versions, right? So you'll have some issues around memory and management in SSI. So this works as long as you have some medium range of concurrency.
So Naga, does that mean it doesn't have any locking, like the range locks that are performed in serializable isolation are not applied on snapshot isolation?
I think they may still have to, maybe index range could still happen, but it won't actually, the locks are there, but maybe they're actually in shared mode. So it just, I think it can use that shared lock concept, like as long as if other transactions are using this or like operating on the same index range, like if you take index range locks, so it can identify from that index range whether if other transactions have committed, like if you have some metadata of which transactions are holding this range locks. I think it can still, it still uses the logs, but not in pessimistic way. It just makes sure, it just uses for them the fact that to check which all other transactions are could be operating in this. So, however, it doesn't um, uh, ask for exclusive logs like in serializable, but it just keeps a watch on them, like which all other transactions are operating in this range. But it still tries to go ahead and going in optimistic way till the commit point. It tries to update, and only before commit it checks whether it's still holding true or not. So
Okay.
yeah,
Thank you.
it still uses that concept, but not like in pessimistic way, just to identify which all other parallel transactions are. Okay, so these are all the three methods of how we implement the serializable. So we can briefly talk about transactions. I think we have about 15 minutes time. Can I talk briefly about them? Like, is everyone okay? I'll probably just give an intro on how the distributed transactions work. We'll not go in detail. So we all know that like all these transactions that we talked about till now is actually on a single node database. So one database server, right? Like as long as you are operating on one database server or like one master where you are writing all these writes, so you are good with these transactions. But what if you have a scenario where like you need to update like the data in two nodes as part of the same transaction? So this could be a database one, and this could be a database two. So in reality, it can be any databases, like they can be same databases or different databases. But you have a transaction, you want to ensure this atomicity of or this transaction guarantees on when you're making update on two databases. So that's a distributed transaction. So where in one step, like you update this, and another step you update this, and when you say commit, and at this point you need to make sure that they're both committed. If not, like you need to abort, right? So we know like this acid makes sure that as long as you are operating on single node, it works. But now when you have multiple nodes, you need to make sure that like you still have this atomicity. So the fact that when we say distributed, these nodes can be somewhere in two different regions or like across the continents. These nodes can be wherever on the internet. So, but you still want to ensure atomicity. So how the distributed transactions normally work is you have this two-phase commit. It is not two-phase locking, but like this is called two-phase commit. This is a protocol which is normally used. So for this to work, you normally have a coordinator An example could be Zookeeper or like some other transaction coordinators. And you have phase one, where you ask all of the nodes to prepare for the commit. And you have phase two, where you actually ask to commit or not. So take an example, let's say you have this coordinator and this is the DB1, this is DB2. So what coordinator does is it normally when any distributed transaction happens, the general idea is it sends the update to both of these databases. Let's say x is equal to whatever, x plus 10 or whatever. It sends to both of them, and then it asks, like in the phase one, it says prepare for commit, and this also prepare for commit. So these two are like phase one. So initially it sends update. Now it's asked like prepare for commit. This is where it is expecting each of the nodes to respond with yes, yes. So when all of the nodes, like there could be multiple nodes here, when all of them responds with yes, then this coordinates makes a decision whether to commit or not. So this makes a decision to make commit or not, commit or abort. If it makes a decision, then it actually sends those decision across again with asking to commit. Then both of them at this point, like though this database crashes, after this makes a decision, it is irrevocable decision. So it's like these nodes have to commit whether now or at some point. Suppose if when sending this commit, if this database was down, so here it goes down. It actually it's a responsibility of coordinator, because whenever this database comes up, you make sure that this coordinator responsibility is to keep retrying until this database comes back and updates successfully. So there are two sorry, I don't know if I'm pronouncing. So irrevocable decisions. So one, when this participants, these are actually called as participant databases. So when this participant gets a prepare for commit request, when they say yes, so it means that they need to take into any other concurrency or whatever the other data issues, ongoing transactions, they need to take everything into account. When they say yes, this decisions from I don't know where is prepare. Yeah, this decisions of each participant is irrevocable decision. So when they say yes to prepare, so this decision is irrevocable. So this is the first step. And when the coordinator makes commit or abort decision, so then this decision is also irrevocable, which means that if coordinator also goes down for some reason, like and this both participants have replied yes, and they'll be waiting for coordinator to send commit request later. So this prepare like transactions which it said yes, and in case if the coordinator dies, and these transactions will have this hanging transactions where they committed yes, and they'll be having them in maybe I don't know some pool, or like maybe they'll have them in their log which are like pending to be committed. So until this coordinator comes back and sends them a commit request, they'll be waiting for commit request. But they won't commit until the coordinator sends them the commit. Was it clear? I tried to explain so much here.
Naga, what is this prepare? Like, what actually database return? I mean, can you actually take this as a real life example, like an updating some table?
Okay, I don't know, like in interest of time. So, I mean, like this is, I'm trying to explain in a generic way right now. We can probably come up with the examples like, suppose if you say, you are having some status of the user here, right? Maybe in, I don't know, like in one database and in other database, it can be in some other form. Some user data you also want to update here. Suppose, I don't know, like you normally tend to partition the data or keep some data in some databases, like in-memory databases, and you have RDBMS. And if you want to make sure that you have a distributed transaction among these two, how would that actually work? We can actually go in details. I just wanted to make sure that you all understand the concept. So you generally need to have the coordinator for this, which makes the decisions on behalf of all the participants. And it is responsible for making sure that all databases commit or abort. So that's a responsibility of coordinator. And again, it's a single point of failure. And these participants, when they reply, so they receive the updates from the coordinator, and as a client, whoever is making the distributed transactions, it could be a web application which is trying to operate on these two databases. It talks to this coordinator. It actually sends these updates. This client actually sends updates to coordinator. Coordinator sends to all the nodes. And when these nodes reply yes, yes, and if one of them says no also, it actually sends a abort request for all of the others. So abort a reset request for all of that. And if all of them reply yes only, then this coordinator will make a decision of yes. So when coordinator makes a decision of yes, it actually uses a write ahead log. We have talked about this previously, right? So this write ahead log just makes sure that for durability, in case if the transaction coordinator dies, it actually crashes. It actually comes back and sees this write ahead log, which all transactions I have made a decision of commit or abort, and I'm yet to execute. So it checks this and actually sends a commit or abort request for all of those. And the participants need to just wait for instructions from coordinator. And these coordinators need to operate on consensus protocols. Like an example, so this consensus is again another concept, like how we ensure how all of this agree to make a decision. Like for some of the transactions coordinators, I think most of them uses this framework called XA. I don't know if you have used this, if you have heard of this term. You have this Java transaction.
Extended architecture?
JTA, yeah, extended architecture. And Java has this JTA concept, like there are few ready-made transaction coordinators available in the market. I think they mostly use this some system APIs to be able to communicate with the coordinator. So there are some language APIs also available depending on the language you choose. We can go and talk about distributed transactions probably in another session also, but I just wanted to give a overview and how it's how the normal transactions are different from distributed transactions. And one of the mechanism is like the two-phase name comes from the fact that there are two decisions which are irrevocable. The one is the participants replying with yes, and they cannot go back on that. and the coordinator making a decision of commit or abort. So this phase, at two phases, this node's participants or coordinator commits on their decision and never goes back on their decision. So that's why the name two-phase commit. It's don't confuse with two-phase locking, which is different.
So question is in two-phase commit, do they, when they say yes, do they perform the action?
No,
when they say yes,
perform.
or
they don't perform. They wait for the commit request from the coordinator. So when they say yes, it may happen that like one of the node may reply yes, the other may reply no, if it has some conflicts on some data or whatever. So if one of them says no, it's for sure coordinator makes a decision to abort. So it sends an abort request to this whichever said yes. And even
but there is no locking involved in this, right? When they say
no
yes,
locking.
they don't lock the resources, do they?
Yeah, no locking here. It's just that they have these transactions ready to be committed.
Okay.
So, but they still need to wait for commit request before it commits the data in database. So, which means that till the transaction is committed, the other transaction, like on this databases, like read-only queries won't be able to read that data. And in microservices world, the other way this distributed transactions are handled is this is like assuming like atomicity, like strict atomicity, like either you do this or don't do this. That's how this two-phase commit works. There is another pattern which microservices use called the Saga. So there, the behavior is like they try to, each of them behave in their own way. Like database, the microservice which is talking to database one, it performs update and on its own. And this microservice which is talking to DB2, it performs its own update. However, if something happens, bad happens in one of the service, there will be another compensating transaction happening in DB1. So the idea of this is the updates do happen, and when it learns that the nodes went out of sync, there will be some compensation or reversible effect. Suppose if the balance got debited and there is in other node it is not, then this balance will be credited back. That could be an example of analogy. So the idea is like you'll have compensating transactions. So you'll have more entries, like the previous update may have still been made, but that effect is reversed with the following update. But this is like a pessimistic, and this is like an optimistic. But like here, you typically have some asynchronous. This is like an asynchronous communication mechanism. How Saga works, like you typically have queues and listeners where you listen that something bad happened and you do a compensating transaction. But this is like a synchronous behavior, and like pessimistic, like either you do everything at once or don't do. But we can actually discuss more about this in any of the future sessions if people have interest.
Yeah, I got an interview question on this time management, like in calendar blocking that we're talking about.
Okay.
In one of the enterprise interviews, they were asking me. They started with how do you design a calendar app of booking system, and then they extended that question saying, now this is a global company. We have multiple offices across the globe. People will be accessing calendar from various locations. So the transactions happen at a very large scale because we have multiple buildings and people can book any building, any room from any place. So they are increasing the scale at that level. And then they're asking me, how do you design a database that can handle this global transactions in a distributed way? Like you have centers across the globe. So I think that is one real world example where we can think about how the transactions are handled at a granular level of a room for a specific interval, how that can be distributed across, because calendars are across the globe and they
Yes.
don't be stored in one single database. It will be stored across in a distributed system. And how you design that is one of the system design questions that I got.
Okay.
Yeah.
Yeah, I mean, like, yeah. So in those, I mean, like, how I would normally approach is like, in those questions, probably you first need to explain how you would address in a single node database,
Right.
and then you go to the how you distribute when this problem, when you scale the system, how you handle. So those are the 2 points you need to, I think, explain like how this calendar booking works. So one of the scenario could be like talking about how that write skews can occur when multiple people try to update or book or reserve the same meeting room, considering the single node. So that gives an like opportunity to explain like how it works in single node, and when we try to expand that to a distributed systems, whether you have, I don't know, this if you want to do in a two-phase commit way or like in the Saga way, and there could be, I'm sure there could be some other ways on which the distributed transactions happen. So for example, the Google Spanner, it's a distributed transaction database which can have databases in multiple nodes. So this spanner actually uses a time concept instead of, I think, locks. I mean, like it uses the, there is a true time.
Synchronized time.
Synchronized time. So it actually uses this time concept to actually synchronize multiple transactions. So the idea is, I think it has some multiple 2-3 vendor GPS, and each of them they'll have at least 3 servers in each of the region. So they will always have the time, and they will have the min and max ranges of time. So at any transaction, whether it began, it actually checks for the time. This is kind of a sloppy time. Like some servers could report that the current time is like 1010 microseconds or something, and some could report that 1020. So this is a variation of time which it uses to see which all other transactions began before, which all other transactions began after, which are all overlapping with this, or like it uses this true time concept to isolate the transactions, distributed transactions. So, and like you were to pick a database, like it could be one of them, Spanner. So it is distributed. Yeah, we can actually talk about that, pick that in one of our weekly sessions and talk about how we design a calendar API and go in deep.
Sure, Naga. Thank you.
So any questions? Like I'll wrap up this session. I think it's 11:10, like 2 hours since we started. Any questions before I wipe off this?
Naga, one other question on that, the serializable snapshot isolation. When we say it checks whether it is in the consistent state and then it applies the commit. So there is a retry mechanism over there, right? So is that the database which does the retry, or is there a middleware involved?
No. The databases doesn't try the retry. It just aborts the transaction, and because there the scenario is like one of the transaction updated, and the other person was not aware about it. So the fact that it was aborted, maybe he was not aware, like the other whoever other user trying to do another transaction, so they will have to retry to the database. Databases simply abort that and send the abort to the client. The client needs to retry, I think.
Okay, so we should set up some kind of mechanism above database to do that retry. Okay.
Yes, correct. Sure. And when you retry, that condition might not be true for the case of like on-call doctors, if you take that example.
Yeah.
Okay, thank you everyone. Like if any questions, like we can still hang on chat. And we can stop the recording now. Let me stop.